Welcome to Learning Labs with Cornerstone. I'm Philip.
And I'm Erica. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
In this pair of activities, students will first discover how thermometers display temperatures in sunny versus shaded areas and why meteorologists always use shaded temperatures to tell us about the day's weather. After that, students will simulate and observe differences in satellites based on orbital position.
Here's what you will need for this experiment. 4 thermometers, or 2 pairs of 2 different thermometers, labeled with permanent marker, number 1 and number 2 for one pair, and 3 and 4 for the other. A pencil or pen, a sunny day in a shaded area. If it's not nice outside, you'll need a desk lamp. As you place the thermometers, make sure that they are always on the same type of surface.
When outside, gather the students in the shade and tell them that today they'll be learning about thermometers and measuring temperature. Walk them out into a sunny area.
Ask the students, what does it feel like in the sun? Does it feel different than when we were in the shade? How is it different?
Place all thermometers in the sun or under the lamp, but not too close. We only want the light, not the heat, to affect the temperature. Leave 2 to 3 minutes for them to adjust.
The sun gives us lots of energy. Have the students stand in an area about 3 feet by 3 feet. When the sun is directly overhead, this area receives over 1,000 watts of energy. That's enough to power a hairdryer or a toaster oven. Most of the energy that gets to the earth from the sun is visible light. Visible light is a type of radiation that we can see. The different colors we see are different wavelengths of visible light. The rest of the energy from the sun is mostly ultraviolet radiation. This is more powerful radiation with shorter wavelengths than visible light. God made our atmosphere to absorb most of it. If we get too much ultraviolet radiation, it can damage our skin, giving us sunburn.
When the ground absorbs the visible light and ultraviolet radiation, it converts it into lower energy infrared radiation. We often experience infrared as heat or cold and record temperatures, infrared radiation, with thermometers. Now that you've waited a little bit, record the temperatures from your thermometers in the sun column of Table 1.
Place all thermometers in the shade or away from a lamp. Leave 2 to 3 minutes for them to adjust.
So we now know that the sun gives us energy as visible and ultraviolet radiation. What happens when it comes and hits the ground, or the thermometers, or us?
Objects in direct sunlight get hit by energy provided by the sun. The object will absorb some of this energy, which increases the energy of the atoms of the object. The more energy the object absorbs, the higher its temperature becomes. The atoms in the object move around or wiggle faster with higher temperatures. Darker objects absorb more energy than lighter ones, because the light colors reflect some of the energy back towards the sun.
So, when the thermometer is in the sun, the energy from the sun is increasing the temperature of the red liquid. Now you're ready to record the temperature of your thermometers in the shade column of Table 1 in your lesson plans.
Show your students their observations on Table 1. Which temperatures were higher, those in the sun or those in the shade? Did all the thermometers display the same temperature in the sun? How about in the shade? Was one pair of thermometers higher or lower than the other pair each time? If so, why do you think they were different?
Calculate the average temperature recorded among the 4 thermometers in Table 2 in your lesson plans. For younger students, tutors can average the numbers. Older students can be asked to calculate the averages in their group. How much variation is there in the individual thermometers compared to the average? Do you think that taking lots of different measurements gets a better or worse answer for the temperature? Do you think that one set of thermometers was more accurate than the other? Why or why not?
A meteorologist is a scientist who studies weather. Television and radio stations have meteorologists to tell us what the weather is and what it will be for the next few days. When a meteorologist tells us the temperature, he uses temperature from a thermometer that is in the shade, not one that is in the sun.
Suppose a meteorologist had his or her thermometer out in the sun. What would happen to the temperature if a cloud came by? Suppose a meteorologist had their thermometer in the shade. What would happen if a cloud came by then? Here's what you'll need for experiment 2. One piece of rope or string, 9 to 10 feet long, 3 students, and an area big enough for a 20-foot diameter circle.
Have 2 students stand at each end of the rope, facing each other with the rope tight. One student will be the Earth and will turn slowly. The other student will be a satellite in geosynchronous orbit. This means that the satellite student will walk in a circle around the Earth student, keeping the rope tight, always looking at the face of the Earth student.
Geosynchronous is made up of 3 Greek roots. Geo, meaning earth, syn, means with, and chronos, means time.
A geosynchronous satellite keeps time with Earth. This means that the satellite always stays over the same point on Earth all of the time and matches the Earth's rotation.
To do this, geosynchronous satellites must be placed very far from Earth, 22,000 miles away, along the line of the equator. At this distance from Earth's center, the satellite moves at about 10,000 miles per hour. That's pretty fast, but it's just fast enough to stay over one place on Earth. Moving faster or slower, or being closer or further away, means the satellite would not stay in the same place above Earth.
Set up like Unit 1, but place a third student along the rope, but only about 1 foot away from the Earth student. This student is in low Earth orbit. They won't hold on to the rope. Instead, as the Earth and geosynchronous student begin to move, have the low Earth student walk in a circle around Earth. But they will take 2 steps for every 1 step the geosynchronous student takes. As the low Earth student orbits Earth, they will need to duck under the rope.
Count how many times the low Earth student orbits Earth in the time it takes for 1 Earth rotation.
Low Earth orbiting satellites are placed 1,200 miles closer to Earth's surface. Some of these satellites and structures, like the International Space Station, are within 300 miles of Earth's surface. This is technically still inside Earth's atmosphere, though the atmosphere is far too thin to breathe, and when working outside, everyone still puts on spacesuits for protection. However, there's enough atmosphere even at these heights that can slow down the satellites a little bit by friction.
Because they are closer to Earth, the planet's gravitational pull on low Earth orbiting satellites is stronger than the pull of the satellites further out in space. To stay up without falling to Earth, these satellites must travel almost double the speed, 18,000 miles per hour, of the geosynchronous ones. Low Earth orbiting satellites will completely circle Earth every 90 to 120 minutes.
What are examples of geosynchronous and low Earth orbit satellites?
Because of their different locations, geosynchronous and low Earth orbit satellites have different tasks and uses. Here are 2 examples for each. Geosynchronous satellites include weather satellites like the Geostationary Operational Environmental Satellite, East and West, record the weather in the United States. Each covers about 2/3 of the country, so there is some overlap in the middle. DirecTV and Dish Network. People who use these satellites for television have small satellite dishes on their house pointing south. This is because the satellites orbit along the line of the equator and don't move their position over the Earth. Some low Earth orbiting satellites include the International Space Station, which was launched in 1998 as a joint effort of several countries. It can hold as many as 6 crew members and currently has 3, 1 US and 2 Russian. You can even see it at night, moving quickly across the sky. The Hubble Space Telescope takes pictures of space for NASA and has been in low Earth orbit since 1990. It has taken over 1.2 million observations.
That wraps up week 1. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.